all you guys in the front row, you'll probably be picked up on the camera. So, greetings and good morning to all of you. I apologize for my tardiness. I also apologize for the business on Wednesday. It was kind of not an especially pretty situation. We had to take my 17-month-old Felix. We had to take him to the Emerge on the weekend because he bumped his head pretty bad, and we were pretty sure he had a concussion in this very hospital, in fact. And we didn't actually get to see a doctor because they had like 30 people in the waiting room, and they were taking people off of ambulances and dumping them in the waiting room. And it was not a very pretty picture, so we decided to get the hell out of there because, like, if it's a concussion, the best thing for it is sleep anyway. So, But anyway, pretty sure that while we were in the hospital, we got exposed to some stomach bug or something like that. And somehow I managed to emerge from such exposure unscathed, probably because I'm the only person in the household without a compromised immune system. My wife's, of course, compromised by pregnancy, and my son's by inexperience. But yeah, so Wednesday morning, I'll spare you the gory details, but it was not looking good. And, since my wife is like 7.5 months pregnant at this point, that type of thing can cause early labor, and you end up in the neonatal intensive care unit, which, obviously is a less desirable outcome. So thank you for allowing me to take the time to deal with that situation. Not that you had a choice. So we're going to make up the time tomorrow. Unfortunately, the 1MD3 class already voted to have theirs at 10:30, so if you wanted to have yours at 10:30, then that's it. Sorry, can't do two at once. So what time do you guys want to do this tomorrow, the makeup lecture?
Late.
6:30.
6:30 at night or in the morning? AM? How many people want to have the makeup lecture at 6:30 in the morning?
So because we can watch the recording, you would have to wake up at 6:30.
Well, I got a 17-month-old, man. I'm up at 5:30 every morning. Yeah, no. How does 9:30 sound? Is 9:30 manageable? I know it's a Saturday, but it will be recorded, so if you can't get up for 9:30 on a Saturday, then you can watch it later.
Do you have any assignments due next week or no?
That's the other thing I'm behind on. I need to take a look and process the assignments.
I will not have time next week. I'm so
There
scared.
will be information regarding the assignments published later today.
Oh no.
Possibly the assignment published later today. We'll see how it goes. Anyway, some of you may have noticed we're a little behind on the lecture material, so I'd like to get the heck moving on it. So today we're going to hopefully finish off this preliminary material on bags, stacks, and queues, and we're going to get into something that's actually fundamental, very fundamental to all of the analyses that we're going to perform on algorithms in this class, which is we're going to talk about Big O and various other mathematical approximations. So, any questions before we get started? Right! So, when last we spoke, we were talking about how you might go about implementing bags, stacks, and queues. In general, we've sort of covered two base data structures from which all kinds of other data structures will be generated. We've talked about the array and the list. In general, you have the traditional trade-off between static and dynamic memory types. If it's something that doesn't change a lot but needs to be read frequently, then you're probably going to want to go with a static data structure such as an array. If it's something that will change frequently and is read from relatively infrequently, then dynamic is your bog. Make sense? Roughly speaking, when we say static arrays, we typically mean arrays that also contain some degree of dynamic growth or shrinkage, just very infrequent relative to dynamic data structure. So if you want a static array which has some degree of dynamism, in general, you should shoot for half of that array being blank at any given time. So if you run out of room in the array, double the size of the array. If your occupation level of the array falls below 25%, chop it in half. The purpose of doing everything by halves, aside from the perennial programmer's obsession with powers of 2, is it makes it a much less frequent thing to have to allocate new memory. And because this is a static data structure where allocating more memory to the data structure may require the copying of the entire data structure into new memory, at worst case, allocating new memory is a big O (n) operation. By only doing this, on doublings, this amortizes that cost over the running of the data structure, which can reduce it to a very, very low percentage of the total amount of runtime necessary to run the data structure. Does that make sense? Any questions about that? So, yes. So in general, when we talk about allocation and dynamic allocation, all of these types of operations, the reference point in your brain should be the dynamic memory operations used in the C standard library because, regardless what language you're using, those are most likely what you're making reference to anyway, which is kind of why it's useful to know C, because by knowing C, you know how the architecture works. Make sense? Good. So, stack using a static array. We have some number n being the size of the stack. We have a push operation adding a new item at asset n, and we have removing an item from asset n minus 1. So, obviously, with a stack, if you remember what a stack is, we're always adding items to and pulling items from the same side of the data structure, right? So that's why we're doing that in this case. Because we are again working with a static array, item lookup is, in terms of runtime, O1, yep, big O1, which is to say it's constant, right? So this is relatively fast. In this example, stack.top refers to the index of the top element of the stack. Further, this pseudocode assumes the array starts at 1 rather than 0. Did I talk about why that is in this class yet? Okay. So 0 indexing for arrays is an implementation detail of, shall we say, current computer architectures. It is conceivable that at some point in the future, either languages will be written or architectures will be defined which do not use 0 indexing, but rather use 1 indexing or whatever. The idea of pseudocode is that these algorithms are independent of implementation, right? So insofar as 0 indexing for arrays is a feature of specific computer architectures, very popular computer architectures, but specific computer architectures, the pseudocode will try to avoid 0 indexing for that reason. Does that make sense? Any questions? Cool. So, as we say, as was given in the diagram previously, if you're pushing items onto the stack, s dot top is incremented, s at s dot top is given the new value. Remember that top is the pointer to the current top element, so that's why we increment it before we write the new element in. Make sense? For pop, if the stack does not actually contain any items, that will cause some kind of error state, which we will call underflow. Otherwise, s dot top is decremented, and we return the item that used to be the top. So here's an interesting feature of this, right? What's conspicuous by its absence in that algorithm? What are we not doing? Yeah.
We're not actually removing it from the stack.
Precisely. We are not actually removing the number physically from the stack. We are simply ignoring that it exists. Why?
I'm guessing the garbage collector will come and like take it away on its own?
Well, the garbage collector won't really care because it's still sitting in an allocated memory space, right?
Next time we push, the data will just get overwritten?
Yes, it doesn't matter. The next time we add something to the stack, that value is going to get overwritten anyway. So to like overwrite it with 0 or a null value or what have you, that's just a waste of time, right? We're going to overwrite that data anyway. It's kind of the same trick that, it's the same trick that C pulls when it's allocating you like memory through malloc, right? It just gives you the memory without clearing it first, because it's assuming you're just going to overwrite it and use it anyway, so what's the point in clearing it? Not to mention clearing data for an malloc operation is, in terms of time, big O of n, so it's linear, right? Because you need to clear each memory cell that you're giving through a malloc operation. So malloc, without clearing, is constant time, with clearing, linear. So that's how it works. And of course, we have a test for emptiness. So if top.s is equal to 0, we return true, otherwise we return false. So there you go. Stack operations using a linked list. So for linked lists, there's kind of, from the array, we want to be placing things at the end of used memory, just because in order to place things at the beginning of that array, we would constantly have to be shifting the items up and down, which costs time, right? So when we have a dynamic data structure where everything is determined by adding nodes to a series of nodes, and it doesn't really cost anything to add a node in terms of moving the rest of the nodes, you can have a stack that makes somewhat more sense with respect to orientation. So in this case, the first element of the linked list is in fact the top of the stack, right? So you could, in theory, maintain a pointer to the end of the stack and access things that way, right? But, why do the bookkeeping if it's unnecessary, right? That also costs time. So, pushed items are prepended to the list. This way, the head of the list is always at the top of the stack. Popped items are removed and returned from the head of the list. Make sense? Are you guys about sick and tired of linked lists by now? I'm really trying. I'm trying to motor through this stuff. They're like, wow, this is him trying to get through material quickly? Wow. So, let's talk about queues. So, for a queue, we have decoupled the entry point and the exit point of the data structure. You feed things in one side and you read things out of the other side. So with a queue, no matter what you're going to do, no matter what you do, if you're using a static data structure, you're always going to be sort of creeping along inside of the array's declared memory space, right? No matter how big you make that array, if you run it long enough, your queue is going to hit the end of it, right? So you must introduce a concept of wraparound, right? That being said, with respect to a queue, it is useful to maintain both a pointer to the head and the tail of the queue if it's inside of if it's inside of an array, right? This allows, if you maintain that, it allows you constant time lookup. NQ and DQ both become constant time, as opposed to having to trace through the array looking for the value you want. Although looking up an item in an array is constant time, finding something, searching an array for something is not, right? So you maintain pointers to the things that you're interested in. Make sense? Good. So NQ adds things at tail, DQ removes things at head. So when the tail reaches the end of allocated space, the pointer wraps around to the other side of the array. Therefore, we cannot assume that the head pointer occupies a higher memory space than the tail pointer. The head might be behind the tail, right? If the head is behind the tail, what does that indicate? It indicates that the queue is currently in a wraparound state, which means that you can't just, trace through to the end, particularly if you're in a language like C that doesn't know how long its arrays are, right? So you have to be careful of that sort of thing. And if we are in a state where the head is equal to the tail, then the queue could be either empty or full, right? So you have to do a little bit of auxiliary bookkeeping on that respect as well.
How would it be full?
Well, so tail is pointing to the next unoccupied space, right? It's not obvious whether, because we're not erasing data as we go, it's like we're not writing nulls in. So we can't just test it to see if it's null, right? We have to, basically, head is pointing to the first used space. Tail is pointing to the next unused space. So if they're both pointing to the same, right, then the next place that you are going to put data might be already used by part of the array, right? Does that make sense?
Yeah.
Cool. Questions?
But is it just is that queue, does that have a maximum number of elements? Like is it 12 and that's all you can do? Or can you just start overwriting the 15?
Well,
Or the 6, I guess, because the 15 started when you decrease.
that depends on what you would want to do with the queue. If you want it to be similar to the undo operation with forgetting that we were talking about previously in class, if you want to forget old elements, then I suppose that's valid, except that it's supposed to be, it's supposed to be a LIFO, right? So what you're doing is you're erasing the next things that were supposed to come out of it, which may or may not be what you want, right? Probably not. If you run out of room in a queue, you really should just allocate more space for it.
So just read it, yeah.
Right? And what factor do you increase the allocated space by when you're allocating more space?
And? Oh, 2.
Double it.
Oh, okay.
Yeah. Question?
So with the wraparound, you just, if you messed up and you said, oh, I thought I would need 12, but I actually needed more, you can't fix that, right? Because it's already wrapped around.
You can fix it, it just takes time, right?
Okay.
What you do, one way that you could do this, right, is you could allocate a new queue, which is larger, and then just dequeue everything out of
Yeah.
the old one and enqueue it into the new one, and then you have a new queue which is larger, which still has all of the elements in the same order, because it's a LIFO queue,
Yes.
right? Yeah, cool. Any other questions? Yes?
When the queue wraps around, how do you find where the tail goes back to? Like, what kind of function do you use for that?
Well, if you're always traveling in this direction, then the tail will always come back to the first element in the array, which of course is, like, in C at least, the pointer to the first element of the array is the array itself, so, you know.
Okay.
So you should always know where the array starts.
Okay.
Yeah. Any other questions? Cool. All right. So, here is your pseudocode implementation of the NQ and DQ operations over arrays. Here, Q, the letter Q is the Q, and X is the item we are NQing. Once again, one indexing is used rather than 0, and that's an explanation of that. So, of course, to NQ something, we assign the current location of the tail the value that we are NQing, and then if the tail is equal to the length, we reset it to the beginning, otherwise we increment it, right? That if statement there encodes the wraparound that we just talked about. Conversely, to dequeue an item, we set x equal to q at q dot head. And at the end, of course, we are returning x. In the middle, we are again checking to see if we have to do a wraparound. Make sense? Good. So, because this is a LIFO queue, both the NQ and the DQ operations move their pointers in the same direction, right? It's like a game of Snake, right? The head of the snake is moving and the tail is moving in the same direction, but the snake is getting longer. You guys do know Snake, right? Yeah. Okay, good. That would have been a whole team. Good. So, queue implementation with a linked list. You maintain one pointer first, pointing to the head. Maintain another pointer last, pointing to the tail. You know what I mean by maintain, right? It means that when you perform NQ or DQ operations, rather than updating indexes, you update pointers instead, right? This is what I mean by bookkeeping frequently. Items are DQ'd from first, items are NQ'd from last. So, you know, in the same way that the stack always is popping elements out in front, this is also popping elements out in front. But because we are maintaining a pointer to the last element of the data structure, we can slap more items onto the end of that in constant time. Make sense? Question?
So that queues and stacks are APIs, right?
They are, well, the API is like a feature of the data structure. The API is a declared interface. The data structure itself is, you know, sort of separate conceptually, if that makes sense.
Okay, just because, like, you know, we talked about some of the data structures, now we're talking about implementation for these data structures as other data structures, so it's a bit confusing, but basically my question is, so now we're like adding pointers, like now we can keep track of the last as well as the first, which isn't something that was like originally mentioned in the definition of like a queue and whatever, so are we like allowed to do that kind of stuff, or will that just make it not a queue anymore for...
I understand your question.
Like,
right?
how strict is the rules is basically what I'm asking.
So long as the interface is maintained, it doesn't really matter what the implementation is. Like, there are better and worse implementations. There are implementations that are better and worse for specific scenarios. But in general, so long as the methods still function the same way they're supposed to. Did you take 1MD3 with me?
Yeah.
You remember the mean calculator example?
The mean?
Yeah, where we had the classes in Python that calculated the average of a set of numbers that came in.
Yeah.
We had two implementations of that. One that maintained all of those numbers in a list, and one that simply kept track of the sum and the number of elements as we went, right? From the perspective of the API, both of those are identical. From an implementation perspective, they are very different. But like for the programmer exterior, right? It's not a matter, like the programmer who's using this software doesn't care necessarily whether you're using static arrays or linked lists or heaps or stacks or frogs. It doesn't matter, right? All they care about is, does this method do what it's saying it does, right? And, you know, if you need more efficiency for one scenario or another, you read more about the documentation, maybe take a look at the code, how they're doing it, choose a more efficient implementation. But from the level of, you know, just putting the software together from a functionality standpoint, these two approaches are equivalent from the perspective of API.
Okay.
So
We're
you see
still
where
behind
this,
it.
sorry?
We're still behind the API. Like we're defining what the API actually does.
Yes,
Okay.
yes,
That makes sense.
yes! We are defining what the API is actually doing.
Yeah, okay.
Yes.
So basically, the specifics of implementation are lost in abstraction.
That's an excellent way to put it. The specifics of implementation are lost in abstraction. If you need more efficiency, you can step into the abstractions and mess around with them, which is kind of like an equivalent operation to like programming in C or assembly language when you need a really, you know, efficient implementation of a particular algorithm. But like from the perspective of, you know, I want this to be abstract and modular so it can go together quickly and reliably, these are not the implementation details we care about from the perspective of the API. Awesome, 2 thumbs up. Any other questions? That was an excellent question, by the way. Any other questions? You're gonna have to shout.
Do we need to know how to implement these with both arrays and linked lists, or can we just like pick one certain thing?
In this class, you should know both. If you're asked in a question, it will either be specified or it won't. If it's not specified, then it's up to you. If it is specified, then you need to use the thing specified. Make sense? Other questions? Okay. I have a slight comic, and then we need to move on to the next topic. Okay? Maybe slightly funny. I really tried with this one. I really tried to capture mimetic energy. I don't know. Fundamentally, when it all boils down to it, I'm just, you know, one more of a set of overly moralized British millennials. Like that kind of characterizes millennials as a caste, I think, is that they're just obsessed with morality. To their own detriment, I think. Anyway, so I hope you appreciate this set of slides because I put a lot of work into it. So we're going to talk about how you actually calculate runtime. I apologize for not getting this to you before your tutorials this week. We're going to talk about we're going to revisit the Big O stuff next week in tutorial now that you're actually going to be taught it, hopefully. So, I don't know, between this class and then 8:30 Monday morning, I don't think there are any tutorials between those 2 times, so I might be wrong. Anyway, so, analysis of algorithms. I've been using terminology so far and just kind of expecting you to have a vague idea what I'm talking about. Some of you, of course, probably have had no idea what I'm talking about. We're going to discuss what Big O actually means in precise, well, you know, as precise mathematical language as your poor humble professor is capable of at a level that's still reasonably interpretable to the students. So, let's talk about analysis of algorithms. So, in general, there are two ways to analyze the runtime of algorithms, just as there's two ways to analyze most scientific questions. You have the empirical methodology and you have the theoretical methodology. Under empiricism, we write the algorithm and we run it and we record how much time it takes, how much memory it takes, its general runtime characteristics. This is tricky. Of course, it's always tricky when you run into reality, but this is not necessarily a reliable way of characterizing algorithms for a number of reasons. Number one, the testing cases that you select for running your algorithm may have a drastic impact on the runtime of the algorithm. And you may, like just because of the state explosion problem, you're probably not going to capture all useful or interesting test cases in your test case set because there are a large number of them, right? You can design tests intelligently, but you can never 100% guarantee that you've had every interesting test case, right? Number two, you may have noticed this, but computer systems vary widely in their power, ability, speed, memory availability. All of these metrics that they use to try to sell you computers affect the runtimes of algorithms. There's really no way, like, a lot of the time you can't even rely on the same computer system to give you consistent results about the runtime of an algorithm, because it also depends on what other programs your computer is running at that time, whether bloody Windows is doing a bloody update, etc. Right? Which it seems to want to do. It seems to want to update more than not it's like its uptime with respect to updates is like 30%. I swear to God. So, contrast this to the theoretical means of analyzing algorithms, which is what we are going to learn here, right? Theoretical analysis of algorithms derives from the structure of the program itself. Our goal is not to exactly predict runtimes. Our goal is to come up with a categorization scheme so that we can determine whether algorithms are good or not relative to other algorithms. This is the same type of language that I've been using so far to discuss the data structures we've been talking about so far. It's like, well, constant time is a lot better than linear, so we should shoot for constant time whenever possible, right? But, linear is itself much better than exponential. Logarithmic is better than linear, but not as good as constant time. We have this system of categorization, and we need to develop how that actually came into existence. So let's talk about what actually affects how long it takes an algorithm to run. So, in general, the total running time of a program is determined by two factors, as first identified by D.E. Knuth, who is sometimes referenced in XKCD cartoons. So, you have the cost of executing each statement, and you have the frequency of execution of each statement. So it's the amount of time each statement takes to execute multiplied by the number of times that statement executes, added to the number of the same calculation for every other statement in the program. This should make a certain degree of intuitive sense, right? It, of course, starts to get complicated when you start complicating the program structure and introducing subroutines and function calls and recursion and all of that. For the purposes of this lecture, we're going to talk about a reasonably simple cases. But this is We'll deal with recursion when we have to. For now, let's just learn the basics. So, overall, our goal is to derive a time function, t at n, which describes the amount of time it takes to execute a program based on the size of its input. Here, n is the size of the input. Normally, in this class at least, this will be the size of the data structure that we are operating on. If it's an array, it is the number of integers in that array. If it is a linked list, it is the number of nodes in that list, etc., etc. Why? Why are we so concerned about the size of the input? Any ideas? You, sir.
We're thinking about scalability, like when we're evaluating these algorithms.
Yes, we're thinking about scalability. It's all well and good for you to have an algorithm running on your computer over, the, grades for like the 200 some students in this class. It's fine. Your algorithm's probably not going to work. It's not going to take too long, regardless, right? But if you're running something like Twitter, which has literally millions of people, tweeting literally hundreds of millions of tweets, we no longer live in an age where we can ignore the existence of very large data structures because, a lot of people live the majority of their lives in these things these days, which is kind of a terrible thing to say about society, but, it is what it is. So, let's analyze swap, right? That 0 through with a slash through it is the empty set. It means that this program takes no arguments. It does, however, require two variables, x and y. You all should know how swap works. So, the execution time of these statements is determined by how many machine code instructions each statement compiles to, or object code. Machine code, object code, same difference. So, in this case, each of these statements is a simple assignment statement with no expression that needs to be parsed or processed. So, it's reasonable to assume that these three statements might take a reasonably similar amount of time to process. But even this can be complicated. At an assembly level, which of these are being stored in RAM and which of these are being stored in registers? Because that affects the runtime. If it's stored in RAM, you have to go fetch it. This is dependent on the manner in which this program gets compiled by whatever programming language you've written it in. So even a program this simple, you can't rely on there being a consistent number of machine code instructions this will compile to, right? So, what do we do in such a case? Well, each statement's execution time is dependent on independent. Each statement's execution time is independent of the values of x and y, right? So, we can write them as constants. Regardless as to how much time it specifically takes to execute line number 3, we know that that is some amount of time. So we're going to assign a variable to that and assume that it's going to be constant, right? We can therefore say lines 2, 3, and 4 will be represented in runtime by constants C2, C3, and C4. We can therefore compose the runtime of the algorithm of C2, C3, C4, plus this mysterious factor CF, which is the function overhead of calling this algorithm in the first place. So, we may notice that we have the sum of a series of constants, right? So this is the case This is a case of an algorithm where we have attempted a representation of each of the runtimes of each of these lines of code, but none of these lines of code are repeated. So we've hit point number 1 on that previous slide, but we've not yet hit an algorithm which exercises point 2. Make sense? Any questions so far? You guys getting this? So far, so good? Can I get a thumbs up? Awesome. So, let's make it slightly more difficult then. So consider linear search. Remember, linear search is an algorithm which traces through every single, every element of a data structure looking for a particular thing and returns true if it finds it. So, let's create a new set of variables, Ci, to represent the runtimes of each line in linear search. Question: how many times is line 3 executed? And remember, despite the fact that we tend to not think of if statements as being like proper statements because they don't mutate memory, when you compile things down to the object code level, they certainly do take time. The expression needs to be calculated, branches need to be jumped to. This takes time in the CPU. So while if statements do not perform direct manipulations of state, they are not timeless operations. Question?
I was going to answer your question.
Oh.
Statement 3 is executed.
Oh, yes, sorry. How many times is line 3 executed?
It could be n or length of a times.
Yes. So the number of times statement number 3 is executed is equal to the number of times that loop is iterated. Right? So, everything, in fact, inside that loop is run once for each iteration of the loop. The number of iterations will vary, however, since this loop breaks once k is found. For now, let's concern ourselves with the worst case scenario. We'll talk about worst versus best case versus average case scenarios a little later on in this very topic. But for now, let's just consider the worst case scenario. In the worst case scenario, the item is either not found at all or found at the very it's found in the very last place you look. Right? So, this loop executes n times where n is the size of a. So, in this case, some of these lines are executed n times. So we multiply the amount of time those statements take by n. Right? So, we're no longer in constant land. This is what's meant by a linear algorithm, because this is a linear equation. Right? So, when we have, polynomial time algorithms, it's because this equation ends up as a polynomial. Right? Does that make sense? We following so far? Good. Yes. Oh, if you're wondering where line 4 went, line 4 and line 5, I'm making an approximation here that you only return once, and I'm taking the runtime of C5 as representative of both of those, so that's where that's coming from in the equation. So, applying this same type of algorithm to bubble sort. How many of you have heard of bubble sort? Okay, good. I was kind of shocked. I did a grep search over all of the material in this course whatsoever, and bubble sort didn't appear once. So I thought I'd put it in. But anyway, so in this case, bubble sort contains a loop that contains a loop. So how many times would we be executing the if statement in this case? N squared. So this would be
Yes.
squared. algorithm. So, the three algorithms we've analyzed so far are extremely simple, and it's already a pain in the neck to keep track of all of these constants. We need to start making some simplifications. So, first, we can simplify our expression by setting some new constants equal to the values of the other constants in sum. Basically, we're taking these, like C3 plus C4 plus C5, and just setting a new constant that's equal to that in the equation, because honestly, we don't really care. These are too variable between computer systems to really give us a good impression of the characteristics of this algorithm. It's this term that's much more interesting and important, right? So our equation for bubble sort becomes an squared plus bn plus c, right? So now we are out of time. Nice. Shoot. Oh, I can't do this now. This isn't the, okay. All right. Thank you, get out of here.